Hi, I'm author and biologist Sean Carroll. Thanks for tuning in. I wish we could be together in person, but COVID has prevented that. Today I'll share with you a few stories from my new book that ask the questions, why is the planet the way it is? How did we get here? Does everything happen for a reason? Or are some things left to chance? Philosophers and theologians have been pondering those questions for millennia. And modern philosophers still do. But nothing puts those beliefs to the test like trauma or a close call. In 2001, Seth MacFarlane was the 27-year-old creator and executive producer of the not yet hit Family Guy. Having made a splash at such a young age, he was asked to speak at his alma mater in Rhode Island. And he tells the rest of the story to Piers Morgan.
A combination of two things. I was giving a lecture at my college the night before and went out with some of the faculty afterwards and had a few pints. And
you got drunk?
Yes. And coupled with the fact that my travel agent had listed the flight on my itinerary as leaving 10 minutes later than it did. And I was generally late for flights. I'd missed a lot of flights prior to that, so it wasn't like it was anything crazily out of the ordinary, but I got to the counter and I said, yeah, I'm booked on flight 11, and the one behind the counter said, I'm sorry, you're too late, they just closed the gate. And I said, all right, well, I'll take the 11 o'clock. Went into the lounge, fell asleep, woke up about 45 minutes later to a commotion, and the first plane had hit, and sat there and watched the second plane hit, and they announced what flight it was, and I turned to the guy next to me and said, my God, that was the flight I was supposed to be on. I was late. I missed it.
MacFarlane was not the only celebrity to miss flight 11. Mark Wahlberg was also scheduled to be on the flight, but changed his plans. And 11 years later, MacFarlane and Wahlberg teamed up to make the movie Ted. Now, what are the odds these two guys would both miss American Flight 11 and later make a hit movie? Were their escapes from mass murder just dumb luck? Or were their lives spared so that our lives would be enriched by a trash-talking teddy bear?
Michelob Ultra Tuscan Orange Grapefruit. My God, America is imploding.
Dumb luck, accident, chance, call it what you will. MacFarlane's late arrival to the airport was purely an accident, albeit an accident with profound personal consequences. What a difference just 30 minutes can make. It's sobering to think what a thin line there is between life and death. And what governs that thin line is a major focus of my new book. Because over the past 50 years, as scientists have learned so much more about the history and workings of the planet, we've been startled to discover how the course of life has been buffeted by a variety of cosmological and geological accidents, without which we would not be here. And as we've probed human biology and the factors that impact our individual lives, we've caught chance red-handed, reigning over that line between life and death. So today I'm going to highlight a few of those events that reveal just how much we live in a chance-driven world, and then briefly explore what that means for how we think about ourselves. So speaking of thin lines, that's exactly what puzzled a geologist working outside the beautiful town of Gubbio, Italy in the 1970s. Geologist Walter Alvarez saw an interesting pattern in a column of rock just outside of town. He noticed that in this large stack of limestone layers, there was a switch in color from white at the bottom to red above. And when Alvarez looked closer, he saw that there was a peculiar layer of grayish clay, shown here where the coin is on the right, that separated the two colors of limestone. Alvarez's decryption of that 1 centimeter thin line began to reveal the story of the most important day on Earth in the last 100 million years. A day that was very, very unlucky for most everything alive, but would eventually turn out to be extremely fortunate for us. And on that day, a long, long time ago, 30 minutes would make all the difference. The Gubbio rock formation was once part of an ancient seabed, so it contained the fossilized shells of tiny creatures called foraminifera, or forams for short, shown here in the electron microscope. These abundant single-celled creatures are part of the ocean's plankton community and food web. And when forams die, their shells settle in ocean sediments and form parts of limestones, which can be later pushed up by tectonic forces as they are in Italy. When Alvarez looked at the forams from the rock cut outside Gubbio, he saw that the white layer of rocks on the bottom contained a diverse array of large fossil forams. But the reddish layer of rock above lacked those species and contained only a few smaller species of forams. And that thin layer of clay in between appeared to lack fossils altogether. Alvarez realized something dramatic had happened in the ocean that had driven many foram species extinct in a short period of time. Now that boundary represented by the clay line, that's also known from terrestrial deposits, like this one from the western United States. The pocket knife is pointing to that boundary, which marks a dividing line between two worlds 66 million years ago. Below the boundary lay the rocks of the Cretaceous period, which make up the last third of the age of reptiles, when dinosaurs ruled the land. Above the boundary lay the Paleogene, which contains no dinosaurs, but marks the beginning of the age of mammals, in which furry animals emerged to become the largest animals on land and in the seas. Alvarez and his colleagues wondered, what on earth could have caused the disappearance of widespread tiny organisms like forams, as well as much larger creatures like dinosaurs? As you most likely heard, it was traces of the element iridium in that thin layer of clay that tipped them off that it wasn't something on Earth, but something from space. An asteroid 6 miles wide and traveling approximately 50,000 miles per hour slammed into the Yucatan Peninsula. The enormous mass of rock blasted out of the crater was hurled in all directions. A thick curtain of ejecta traveled at several thousand miles per hour and rained down across North America, while the impact plume, consisting of superheated air, carbon dioxide, water and sulfur vapor, vaporized rock, chunks of target rock, that shot ejecta at velocities greater than the Earth's escape velocity, more than 25,000 miles per hour, into and beyond the atmosphere, which then fell back down across the globe as trillions of red-hot meteors. The result was hell on Earth. The falling ejecta heated the air to 400 to 600 degrees Fahrenheit, like a baking oven, and triggered global wildfires. The impact plume and soot from the wildfires blocked out the sun. Global temperatures then dropped by at least 20 degrees Fahrenheit, probably more. Food chains collapsed. And this blackout lasted for at least 10, perhaps as many as 30 years. During that time and afterwards, 3/4 of all plant and animal species on Earth, including the great dinosaurs, went extinct. But this asteroid impact is the mother of all accidents. And that's because we've come to appreciate that there were pretty special circumstances for this mass extinction to happen. The destructive power of the plume depends upon the mineral content of the impact site. And geologists have figured that only 1 to 13% of the Earth's surface contains the right kinds of rocks to trigger a mass extinction if vaporized. So what that means is with the Earth rotating at 1,000 miles per hour, had this asteroid, which had been circling the solar system for perhaps 4 billion years, had it entered the Earth's atmosphere just 30 minutes earlier, it would have landed in the Atlantic. 30 minutes later, it would have landed in the Pacific. And in either case, there would be no mass extinction. The dinosaurs would still be here, and we would not. And of course, there would be no Ted, and God forbid, no Ted too. Now let me show you another collision. This one's a little more personal. In this clip, the collision at the upper right also triggers a shower of chemicals. But this time, life does not end. It begins. Because this is the moment of fertilization. The trembling and shower are part of the sequence of dramatic physical and chemical changes that occur in the egg that prevent fertilization by other sperm and begin the process of embryonic development. Out of a swarm of 100 million or more contenders, only a single lucky sperm will swim all the way up the fallopian tube and successfully fertilize the egg. The fertilized egg is the union of two genomes, half of its chromosomes from the sperm and half from the unfertilized egg. Now here's an astounding fact. No two fertilized human eggs will ever be the same. That's right. Ever be the same. To see why, let's try a pop quiz. You ready? So, by each contributing 23 chromosomes, how many genetically unique children do you think your parents could have? 23? 46? Maybe 92? No, try again. How about 70 trillion? That's right, 70 trillion. And what that means is that each one of us, is a 1 in 70 trillion event. Which means that fertilization, well, it's the accident of all mothers. To see why, let's break down the math. The number of possible chromosome combinations from dad can easily be calculated because you can give two different versions of each chromosome, and there are 23 chromosomes. And so there are 2 to the 23rd power, or 8,388,608 possible chromosome combinations from dad. Same math for mom. 23 chromosomes, 2 alternatives for each chromosome, 8 million plus possibilities. But the number of possible combinations of sperm and egg, the number of possible combinations would each create a different child, is the product of those two numbers, which gives you 70 trillion, 368 billion, 744,177,664 unique children. After my arrival at 10 pounds 5 ounces, my mom stopped at 4. But this enormous number is actually an underestimate because of another important contributor: mistakes. I'm talking about the copying of DNA, 3 billion letters in each sperm, 3 billion letters in each egg. Heck, it's so easy to make mistakes with much shorter lines of text. Let me show you a couple of my favorite examples. So, I'm a passionate baseball fan, started when I was a kid, and in the early days, I read the sports pages every day. And when I saw this story in 1974, I clipped it out and kept it forever. There are 3 mistakes in this very short sports article. See if you can spot them all. All right, you ready? There's the first one. There's the second one. And yep, there's the third one. That must have been quite a wallop. I don't think these were intentional. These are random mistakes, typos. Here's another howler from a slightly higher authority than the Toledo Times. This is the 1631 version of the King James Bible. And I'm drawing your attention to the 7th commandment. I'm pretty sure this is the copy of the Bible that's in the White House bedroom. The blasphemy was not detected for a year. And King Charles I was, well, he was royally pissed. He ordered that all copies be burned. He revoked the printer's license, one of whom died in debtor's prison. What a difference a single letter or word can make. The same is absolutely true in life's alphabet. Let me show you what a difference one typo can make. I'm going to show you a very short piece of genetic text. The original line reads this singular letter code. And just one typo, changing that middle M to R, has killed more than 33 million people. Now, how could such a small change be so deadly? I'll tell you that in a few minutes. The crux of the matter is the cause of that change. And that leads us to the DNA molecule. Now, this is the structure on the left that was worked out first by Watson and Crick in 1953. And the key breakthrough was the discovery of the rules for the pairing of the bases that hold the double helix together. G with C, A with T. They're located on the opposite strands of the double helix. Now, a footnote to that discovery is actually of central importance to my discussion today. So, fair warning, I'm going to talk a little chemistry because the details are so revelatory. Don't worry, you're going to get the gist of it. It turns out that the bases occur in two alternative chemical forms. They differ by the position of one hydrogen. Okay? So in the top form, you can see that the oxygen up there in red does not have a hydrogen bound to it, but in the bottom form it does. Similarly, you'll see a hydrogen up above on that nitrogen that's lacking down here. And this is called the keto form and the enol form of these bases. At first, Watson only knew about this less common form, the enol form, and that stumped him. But he learned from a colleague that the keto form is actually the more common form, and history was made. The important detail, however, is that these two different forms, they bond with different bases. Now, only very recently has it been possible to capture and measure the transition between the two forms in DNA. And that reveals something very important. The enol form is fleeting. It's flickering back and forth. Enol, keto, but the enol form lasts only about 1/1000th of a second before flipping back to the keto form. And you might say, well, so what? Well, the so what is, if that happens where the DNA is being copied and the copying machinery is passing by, moving at about 1,000 bases per second. If it just happens by chance to pass when the enol form is present, well, the wrong base gets inserted. And that creates a mutation. So that flickering is random, and it's just a matter of chance of whether that DNA is being copied at that moment. So this is the process of random mutation. It's fundamentally what's happening. And what does it tell us? It tells us the event at the root of mutation is an inescapable fundamental matter of physics. This quantum transition between chemical states, a little chance shapeshift at the atomic level. And that tells us that mutation is a feature, not a bug in DNA. In every organism, in every cell, whenever DNA is copied, changes will occur because of the intrinsic characteristics of the very bases that endow DNA with its properties. Change, evolution, it's unavoidable, inevitable. Now, of course, because every species' DNA is different, because of this process, every individual DNA is different. It's changed in this way. This tells us that chance is the source of all innovation, all beauty, all diversity in the living world. It's pretty hard to imagine, isn't it? How can chance generate everything we see in the living world? Well, that's a long story, but let me just show you one example of how chance invents. And speaking of beauty, get a load of this guy. Okay, the most important thing about the Antarctic eel pout is not how it looks, but where it lives. It lives in waters that are very cold, about minus 1.8 degrees Celsius, below the freezing point of fresh water. It lives in the Antarctic Ocean. And the main enemy of fish in these waters is not so much the cold, but ice. The water contains small ice crystals that if they get into the fish through its gills or get swallowed, that will nucleate the formation of larger ice crystals, and bam, they're fish sticks. It would freeze the animals were it not for a key invention. And that invention is antifreeze. Eel pout blood does not freeze until it reaches about minus 2.1 degrees Celsius, colder than the ocean. The reason being that it's chock full of proteins that work as antifreezes. The antifreeze binds to small ice crystals and prevents them from growing larger. And it lowers the temperature at which those ice crystals can then grow. Now, the really neat part of this story is that we can track the origin of the genetic code for antifreeze, how it evolved from an entirely different gene, which gives us a forensic trail of how this invention arose, and it shows how chance mutation is an inventor. Now, a key clue came when it was noticed that the antifreeze protein bore an uncanny resemblance to a section of another protein found in other fish, in fact, in all sorts of other animals. The protein is an enzyme called SAS that's involved in the making of a specific sugar. We're not going to get into those details. The antifreeze sequence is very similar to a short sequence at the end of SAS, over there at the tail end. Now, the reason for this strong resemblance was deciphered by some expert sleuthing through the DNA of eel pouts and other fish. And that detective work revealed that the antifreeze gene evolved from a chunk of the SAS gene. A mutation deleted really sort of the core of the SAS gene, leaving behind the part that had some ice binding activity. That remaining chunk encoded a protein that on its own could bind to ice crystals. And that was the genesis of the first antifreeze gene. The eel pout's ancestors then ran, or rather swam with this invention, and made many copies of the antifreeze gene, expanding it to more than 30 copies, which enables the fish to make a lot of antifreeze. So if you look along the genome, along the chromosome of the eel pout, you see these other genes just like other fish have, and then this, boom, this battery of antifreeze genes. It's a telltale sign that this is a peculiar adaptation to where it lives. The eel pout has over 30 copies of this gene, all tandemly arrayed, and that tandem arrangement tells us there was another mutational mechanism at work that we know quite well that duplicates individual or blocks of genes. Now, I could show many more examples of the creativity of mutations. I'll spare you and let this one make the point that mutation, thus chance, is the inventor. And what this means is, as you look around the world, is that we live in a world of mistakes governed by chance. Genetic accidents occur at random. They change genes without regard to the potential consequences. Now, the eventual fate of those mutations, well, that depends on external circumstances. In a sieving process we call natural selection. Fair to ask then, what determines those external circumstances? So let's look at the eel pout example. The most relevant thing about the eel pout is the coldness of the Antarctic Ocean. So we ask, how and why did the Antarctic Ocean become so cold? The answer involves tectonics. You may know that the Earth's oceans and continents are on tectonic plates that move around the globe very slowly and have moved over time. And with respect to the Antarctic, a couple plates are most relevant to becoming cold. And that involves the former joining of the South American and Antarctic continents that were joined at least 65 million years ago, and the position of the Indian subcontinent, which 65 million years ago was below the equator, whereas today it's now up in Asia. It was that collision of the Indian subcontinent that triggered global cooling and glaciation of the Antarctic. And the separation of Antarctic from South America isolated the Southern Ocean and led to cooler currents circulating the continent. Okay, so I'm talking about tectonics, but then you might ask, and why did these plates move in the way they did? Well, the movement of these plates has to do with their size, their shape, and their speed is determined very much by their thickness. So, why did these plates move the way they did? Well, they were parts of a supercontinent, Gondwanaland, 140 million years ago, that broke up. And from what we can tell, it broke up much like a kitchen plate breaks when it hits the floor. It broke into random pieces. Some of those pieces were larger, some were smaller. The smaller pieces, like the Indian subcontinent, moved more quickly and slammed into other continents. So what's that tell us? The size, shape, and speed of these plates is a matter of chance. So what does that tell us is that chance invents. This internal mechanism based on DNA is the inventor. And the fate of that invention depends upon external circumstances shaped by chance. We're a long, long way from Providence, and I don't mean the capital of Rhode Island. It is astonishing that blind chance is the source of all novelty, diversity, and beauty in the living world. I hope that you are awestruck at what an asteroid, sliding tectonic plates, and a flickering polymer of just 4 bases have wrought. But our chance-driven existence also poses the unsettling quandary that we don't live in the best of all possible worlds, just our world. And this view, of course, shatters traditional beliefs about cause and effect in our world. Those beliefs are represented, for example, by this book and quote from theologian R.C. Sproul, who categorically rejects the existence of chance in his book, Not a Chance, The Myth of Chance in Modern Science and Cosmology. Sproul says, "It's not necessary for chance to rule in order to supplant God. Indeed, chance requires little authority at all if it is to depose God. All it needs to do the job is to exist. The mere existence of chance is enough to rip God from his cosmic throne. Chance does not need to rule, it does not need to be sovereign. If it exists as a mere impotent, humble servant, it leaves God not only out of date, but out of a job." All right, so according to Sproul, chance puts God out of a job, or at least many of the jobs we've traditionally assigned to him or her. God is not in the conception business, choosing the winning sperm and egg, nor the genetic engineering business, designing creatures' DNA and traits, nor the weather-making business, nor the cancer business, nor, as it turns out, the pandemic business. Remember that piece of code I showed you before about how much difference one typo can make? Well, now I'll reveal to you that the original text, those 9 letters I'm showing you, is a small part of a virus called the simian immunodeficiency virus that infects, for example, chimpanzees. And that the altered text with that one typo is the corresponding part of the human immunodeficiency virus, the HIV virus. And what we know about that change is that that mutation, leading from M to R, enables chimpanzee virus to infect humans. And that has occurred by accident at least 3 separate times and triggered the AIDS pandemic. What a difference one typo can make. So if not theologians, who do we turn to think about chance and its implications? So I choose novelist Kurt Vonnegut. Now Vonnegut wrote a lot about our accident-driven world and our struggle for meaning in many of his works. And I want to share with you one particular story that comes from his semi-autobiographical novel, Slapstick. He explains that his sister Alice was dying of cancer at the age of 41, and he and his brother went to visit her on what turned out to be the last day of her life. And he wrote, "Hers would have been an unremarkable death statistically if it were not for one detail, which is this. Her healthy husband, James Carmel Adams, the editor of a trade journal for purchasing agents, which he put together in a cubicle on Wall Street, had died 2 mornings before on the broker's special. The only train in American railroading history to hurl itself off an open drawbridge." Think of that. This really happened. Now, the great humorist concocted many fantastic scenarios in his books, but this really did happen, just as he said. The train plunged off an open drawbridge, killing 48 people, including Vonnegut's brother-in-law. Now, he and his brother decided they would keep this information from their sister Alice because she was, of course, concerned about the future for her children. They had 4 children together. But another patient told Alice about the accident. She read the newspaper and saw her husband among the list of victims. And her response to that? Vonnegut writes, since Alice had never received any religious instruction, and since she had led a blameless life, she never thought of her awful luck as being anything but accidents in a very busy place. Good for her. Accidents in a very busy place indeed. We now know that we are all here, both collectively and individually, through a series of accidents, cosmological, geological, and biological accidents. Vonnegut's books helped me to realize that next to scientists, the one group of people that seem least inclined to think everything happens for a reason, rather that blind chance governs the world, are humorists and comedians. So many great present-day comedians, Seth MacFarlane, Eric Idle, Bill Maher, Ricky Gervais, Sarah Silverman, and many more. And late greats from Mark Twain to Vonnegut to George Carlin have rejected traditional beliefs about cause in the world. So many very funny people, in fact, that it made me wonder, why is this so? What do scientists and comedians have in common? Why are comedians drawn towards such subjects? I reached out to several, some of whom kindly took the time to reply. And I'll leave that conversation for those who want to read the book. But I'm going to close today with a couple of gems from two comedians. The first comes from Ricky Gervais, who told 60 Minutes the following. It always comes back to us. Why are we here? Well, we just happen to be here. We couldn't choose it. We're not special. We're just lucky. And this is a holiday. We didn't exist for 14.5 billion years. Then we got 80 or 90 years if we're lucky. And then we'll never exist again. So we should make the most of it.